Hey everyone, so I was just kidding about that last video being the last video of the chapter. I forgot that of course we need to go through some AP practice problems. So what we're going to do today is go through 3 FRQs that have questions largely focused on volumes of revolution, but of course they could include area and some other things like that. So we're going to look at 3 old AP questions, and then tomorrow in class we'll be working through some AP questions for practice. So let's see what we've got here. For this first one, taken from the 1998 AP exam, this is a calculator question. It says, let R be the region bounded by the x-axis, the graph of y equals square root of x, and the line x equals 4. So the first thing we're going to do, I always sketch a graph of the region that I'm working with. So y equals square root of x. Something like that. And I know I'm bounded by the line x equals 4. Okay, so by the x-axis, y equals square root of x, and the line x equals 4. So now I know my region here. So for part A, all I need to do is find the area of the region R. So since I'm dealing with this region, the easiest thing to do here is just going to be to work with top minus bottom. So we're going to integrate the top minus the bottom. So my area is going to be the integral. Now let's see, I'm going from 0 to 4 because I'm going to integrate with respect to x. 0 to 4, remember my integrand is just top minus bottom. So technically square root of x minus 0, which really we're just integrating from 0 to 4, square root of x dx. And so we're going to use our calculator to do that. Integral 0 to 4, square root of x dx. Okay, and so that's approximately 5.333. Now for a calculator question, putting the rounded answer is fine. We could also, I guess for this one it's not going to turn it into a fraction. So since it's calculator, like I said, the rounded answer is fine, and we're going to go to 3 decimal places. Now, part B is a little twist on things. So it says find the value of h such that the vertical line x equals h divides the region R into 2 regions of equal area. So the idea is that there's some line h here. So I'll label that x equals h. And the idea is that if I integrated from here to here, I would have the same area as the integral from here to here. So there's 2 ways I can go about this. But here's how I'm going to set it up. I know if those regions have to have equal area, then I know that the integral, let's see, the integral from 0 to h of the square root of x dx has to be equal to the integral from h to 4 of the square root of x dx. Right? That's telling me those integrals are comparing those areas, and so if I set that up, I know those areas are going to be the same. So now this is x to the 1/2. So if I anti-differentiate that, I'm going to have, if I add 1, I get x to the 3/2, and I need to multiply by 2/3. So from 0 to h. And I know that has to equal, my antiderivative is going to be the same, 2/3 x to the 3/2 from h to 4. So this one is going to be just 2/3 h to the 3/2. This here, we're going to have 2/3 h to the 3/2, or excuse me, sorry, this is going to be 4. Let me write this again. 2/3 times 4 to the 3/2. I'm evaluating at my upper limit, and then I'm going to have minus 2/3 x to the 3/2. Why did I put an x there? I'm going to substitute my h. Okay, so I know these 2 quantities have to be equal. So I'm going to get all of my h's on my one side. So if I have subtract, I'm going to add. So I have 4/3 h to the 3/2. Now over here, I know that the square root of 4 is 2. 2 cubed is 8, so this is going to be equal to 16/3. Okay, now I'm going to try and solve for h here. So I'm going to multiply by 3/4 on both sides. So I have h to the 3/2 is going to be equal to 4. So now I'm going to raise this to the 2/3 power. So I have h is equal to 4 to the 2/3, right? Which is going to be the same as 4 squared is 16, so the cube root of 16. Okay, so the value of h is just going to be the cube root of 16. All right, now I used kind of a lot of room here, so I'm just going to jump to a separate piece of paper for part C so we can see the problem. Okay, now part C is just back to a volume of revolution here. So part C is asking if I rotate that solid or evolve that solid about the x-axis. So again, I'm going to draw my solid or my curve. So there's my one boundary and my other boundary. I'm revolving about x. And again, looking at this, there's no space in between my region and the x-axis. So I know this is just going to be a simple disks problem. There's going to be no hole here, so I don't have to worry about two different radii. So now, let's see. We know our radius of our cross sections is just going to be the top minus bottom, so it's the square root of x. So our area in terms of x is just pi times the square root of x squared, or pi x. So now our volume is pi times the integral. Our limits are x values, so from 0 to 4 of x dx. Now, that would be a simple one to anti-differentiate by hand, but since I have a calculator, I'm just going to go ahead and use it. So math 9 from 0 to 4 of x dx. And I get approximately 25.133 for that volume of revolution. Okay, so now the last part says I have a vertical line x equals k that divides the region into two regions such that when these two regions are revolved about the x-axis, they generate solids with equal volumes. And we need to find the value of k. So this one's really similar to our other problem. So what that's telling me now for part D, I should label this part C here. For part D, it's telling me that if I were to take the integral from 0 to k of x dx, that should be the same volume that I get if I integrate from k to 4 of x dx. Okay, so now we're going to do a little bit of work to solve for that value of k. So I'm going to have pi times, we have x squared over 2 from 0 to k. On this side, we're going to have pi, still x squared over 2, and we're going from k to 4. So this is just going to be pi times k squared over 2. That's going to be equal to, let's see, 4 squared is 16 divided by 2, so I'm going to have 8 pi minus, and again, I'm going to have my pi times k squared over 2. So now I'm going to add this over here. So really I have, let's see, pi k squared over 2 and add 1. I'm going to have pi times k squared is equal to 8 pi. I'm going to cancel a pi from each side, and I know that k is going to be equal to the square root of 8. So if I were to draw on a line at x equals the square root of 8, then I would be creating two solids with equal volumes if they were revolved around the x-axis. Okay, so that's it for that question. We're going to move on to the next one. Okay, so this one is from the 1999 exam. Okay, this looks like a region we've actually worked with quite a bit in some other problems that you've done. So we're bounded by y equals x squared, and then above by y equals 4. First thing we're going to do is just find the area. And again, this one's a very easy candidate for just doing top minus bottom, integrating with respect to x. So our area is going to be the integral. Now my intersection points here, really I'm looking for where is x squared equal to 4. So we know we're going to have positive or negative 2, so those are going to be my limits of integration. And we're going to do top minus bottom. Now in this case, our top is 4. My bottom is my function x squared. So my integrand is 4 minus x squared. We're going to have our dx. And again, this is a calculator question, so I'm just going to go ahead and use my calculator. Let's see, negative 2 to 2 of 4 minus x squared dx. So I'm going to get 10.667, or I could put 32 thirds. Either one of those, sorry, this was like in the glare here. Either one of those would be acceptable for the exam. Okay, part B. We want to find the volume of the solid generated by revolving this region about the x-axis. So now if I look at this problem, I can see that this is going to be a washers problem, because now I have this negative space between my region and the x-axis. So my big R is going to be here, and then I have my little r in this negative space. So for this problem, my big R is just going to be 4 minus 0, or 4. My little r is going to be my function x squared minus 0, or just x squared. So now to find the volume, we know we have to do pi times the integral. Again, my limits are negative 2 to 2 because I'm going about x. I'm going to have my big R squared minus my little r squared, and I'm integrating with respect to x. So if I do my integral, move this down where you can see here, negative 2 to 2 of 16 minus, that would be x to the 4th, dx. So I'm going to get 256 over 5, and multiplying that by pi gives me 256 pi over 5. Okay, nice straightforward questions so far. So now for part C, it says there exists a number k for k greater than 4, such that when r is revolved about the line y equals k, the resulting solid has the same volume as the solid in part B. So the idea is, if I revolve it about some line, maybe I'll draw the picture again here just so we don't get confused by our different r's. So for part C, I'm going to take my same region here. So I'm still bounded by y equals 4. But now it says I'm revolving about some line y equals k, where k is greater than 4. So maybe it's something like this. This is my y equals k. And the idea is that if I revolve about that line, I would have the same volume as the volume in part B. So it asks us to write but not solve an equation involving an integral that we could use to find the value of k. So now all we have to do is treat this just like our normal volume problems. So if I'm revolving about y equals k, that's parallel to the x-axis, so I'm still integrating with respect to x. And what I also notice is that I have negative space here between the line that I'm revolving about and my region. So this is going to be a washers problem. So if I were to just grab another color here really quick, I've got my big R from there to there, and I've got my little r here. So if I look at this problem, my big R is going to be my top, which is now k. The bottom is my curve, so k minus x squared. And my little r is just going to be k minus 4. So now my volume is going to be pi times the integral. My limits are still negative 2 to 2. I'm going to have my big R, k minus x squared. I'm going to square that, and I'm going to subtract the square of my little r. So that's the integral. Now, it says it should have the same volume as the volume in part B. And the key here, remember, if it asks you for an equation, make sure your answer is an equation. So far we have an integral, but we need to say, well, this volume should be equal to the volume from part B, which was 256 pi over 5. So that's our equation that we could use to solve for k. All right, one more for this video. We're going to look at a question actually that came off of last year's AP exam. Okay, so they're saying the inside of a funnel of height 10 inches has circular cross sections. So you can think of this, if we look at 1/2 of this shape, you can think of this curve being revolved around the y-axis to give us a funnel shape. And they're giving us the radius here. So it says at any height h, the radius is given by this function. Okay, so again, we're just thinking of a function that's being revolved around y to give us this funnel shape. Okay, and it's telling us the units of r and h are inches, so we're going to want to make sure that we include those units in our answers. So for part A, all it wants is the average value of the radius of the funnel. Well, we know how to find the average value. Remember, the average value is just 1 over b minus a times the integral from a to b of whatever function we have. So in our case, and I should have made note here, this is no calculator, so we're going to have to do some work on our own. So the average value here, so it's defined h is between 0 and 10. So for part A, I'm going to have 1 over 10 minus 0 times the integral from 0 to 10 of my function here. So 1 over 20 times 3 plus h squared dh. So now, let's see, I know this is 1/10. I'm going to bring my 1/20th out front. So if I multiply those, I have 1 over 200. Now my antiderivative is going to be 3h plus h cubed over 3. And we're evaluating that between 0 and 10. So I have 1 over 200 times 3 times 10 is 30, plus 10 cubed is 1,000 over 3. And then if I were to subtract 0, that's just 0, so I don't have to worry about it. So this is going to be 1 over 200 times, I'm going to make this a common denominator of 3, which is going to make this 90. So I have 1,090 over 3. So now if I multiply, I have 1,090 over 600. And I'm just going to divide each top and bottom by 10. So I'm going to get 109 over 60. And those units are inches. So my average value of the radius is 109 over 60. And again, our units are inches. Okay, part B. We're going to find the volume of the funnel. Okay, well, we're already told what the radius of that funnel is. So I know I just have to do pi times the integral from 0 to 10 of my function. Now notice my y-axis really, right, is my h-axis. Since my function is already in terms of h, I don't need to worry about doing any rearranging. So my volume is just going to be pi times the integral from 0 to 10. Now remember, I have to square my whole radius, so I keep pointing to it and you can't see that. I have to square the whole radius, so we have to make sure that we square that 1/20th as well. Sorry, h squared, and we're going to square this whole thing, and we're integrating with respect to h. So let's see what happens here. If I square 1/20th, I'm going to get 1 over 400. So I'm going to pull that out front. I'm going to have pi over 400. Now I have to integrate from 0 to 10. Squaring this quantity, remember, I'm going to get a trinomial here. So 3 squared is going to give me 9. Then I'm going to have plus 6h squared plus h to the 4th dh. So I get pi over 400. Now I can anti-differentiate. So 9h plus, let's see, 2h cubed plus h to the 5th over 5 from 0 to 10. And now we just have to do some arithmetic here. Pi over 400, now I have 90 plus, let's see, 10 cubed 1,000 times 2 is 2,000. Plus 10 to the 5th, let's see, we get 100,000. 2, 3, 4, 5 over 5. And now to simplify, pi over 400, this is going to give us 2,090. 100 divided by 5 is going to give us 20,000. And let's see, pi over 400 times, what do we get? 22,090. Now I'm going to divide by 10 on top and bottom. So I get 2,209 pi over 40. Oops, sorry. I haven't been paying attention to the paper. So 2,209 pi over 40, and since this is volume, my units are inches cubed. All right, and one last piece to this now, and I'm going to cover this up so I can get the problem back in view here. So now it says the funnel contains liquid that is draining from the bottom. At the instant when the height of the liquid is h equals 3 inches, the radius of the surface of the liquid is decreasing at a rate of 1/5 inch per second. At this instant, what is the rate of change of the height of the liquid with respect to time? Hopefully this should sound familiar. I know it's been a long time, but this is our related rates problem. Right? When we're looking at the rate of change with respect to time. So we need to know, let's see what we've got here. We've got our radius function is 1/20th times 3 plus h squared. We need to find the derivative with respect to time. So we're going to use our implicit differentiation. So dr dt. Well, if I'm finding the derivative of this, I know a constant times a function. Its derivative is just the constant times the derivative of this function. So my 1/20 is going to stay, and now I'm going to differentiate. Well, the derivative of 3 is just 0. The derivative of h squared is going to be 2h, but now I need to differentiate with respect to time, so I'm going to have a dh dt. And if I clean that up a little bit, what I'm going to have is 1/10 times h dh dt. So now we just need to look and see what we know. It looks like I have a dr dt. I need to know an h. I've got a dr dt. And I've got dh dt. So let's see what we know and what we have to find out. So my problem is telling me at the instant when the height is 3 inches, so that's going to go there. says the radius of the surface of the liquid is decreasing. That means my dr dt has to be negative 1 over 5. And since they're asking for the rate of change of the height, our dh dt is unknown. So let's plug in what we know. dr dt we found out was negative 1 over 5. That's equal to 1 over 10 times our h was 3, and dh dt is our unknown. So now I've got negative 1/5 equals 3/10 times dh dt. I'm going to multiply by the reciprocal to get rid of that. So this cancels, and I get dh dt equals 10 divided by 5 is going to give me 2, so negative 2 over 3, and I know this is going to be inches per second. So you can start to see, even though these are largely area and volume problems, they might pull in some related rates or some other kind of novel questions as well. So that's it for today. Thanks for hanging in with a slightly longer video, and we'll get some more practice in class tomorrow.